In this video, I'll be demonstrating the process of how to actually find the critical points of a function of two variables. We're going to start with this one. F of xy is equal to x squared plus y squared minus 12x plus 8y plus 3. Now, in order for us to find the critical points, we have defined this as where a directional derivative is equal to 0 for any direction. We can boil that down to simply taking a partial derivative with respect to x and setting it equal to 0, and a partial derivative with respect to y and setting that equal to 0 as well. Differentiating with respect to x, the x squared will give us 2x. The minus 12x will give us minus 12, and all of the other terms are either constants or being treated as constants for this partial derivative. As such, that's all that we need. Well, for the partial derivative with respect to y, the y squared will give us 2y, the 8y will give us plus 8, and every other term is either a constant term or being treated as a constant, so those will all go to 0. Now, solving this system of two equations with two variables is not going to be particularly difficult because they are both linear. Now, it should also be pointed out that if we were to change the f of xy into a z, then the corresponding traces, the xy trace would be a circle, the xz trace would be a parabola opening upward, and the yz trace would be a parabola opening upward as well. That lets me know that this is an elliptic paraboloid that opens in the upward direction. So the critical point of 6, negative 4 is a minimum. And again, we could probably complete the square to figure out what this all looks like. Something like f of xy is equal to, if we take the x squared minus 12x, add 36, it'll complete the square. Take the y squared plus 8y plus 16 will complete the square. And then to balance those out, we would subtract 36 and subtract 16, letting us know that this is x minus 6 quantity squared plus y plus 4 quantity squared. And then, oh boy, that's going to be minus 49. So yeah, the vertex of this elliptic paraboloid is going to be located at 6, negative 4, negative 49. And that's how we can tell that it is a minimum value. So that's more of a graphical or a geometric interpretation of what this is, as opposed to what we're going to see in the next problem, which would be the following. We're going to find all critical points of f of xy is equal to x minus y times 1 minus xy. So first thing I'm going to do before I start taking partial derivatives is expand, doing a little bit of algebra. So this would be x minus y times 1, and then x minus y times negative xy. That'll become negative x squared y plus xy squared. Yeah, that looks right. Now we'll take a couple of partial derivatives. Partial derivative of f with respect to x will be equal to x becomes 1, minus y will go to 0, and we'll see a minus 2xy, and plus y squared. That'll be equal to 0. Then for the partial derivative of f with respect to y, this is where we would see that'll be 0, that'll be minus 1, and we'll see minus x squared, and we'll see plus xy squared, or excuse me, plus 2xy. And that leads us once again to that being equal to 0. Now the algebra that we're going to go through this time is going to be a little bit more complicated than what we went through last time, especially because these are now nonlinear equations. I would like to point out, though, that if we add these two equations together, we can get some of the more complex terms to cancel each other out. So what I'm going to do is add the equations. So 1 and negative 1 will cancel each other out. Negative 2xy and positive 2xy will cancel each other out. We'll be left with negative x squared plus y squared is equal to 0. This can also be interpreted as y squared is equal to x squared, so then y would be equal to plus or minus x. This will allow us the opportunity to go ahead and plug these in to the original two equations as sort of a substitution. So if y is equal to x, I should get the same result of plugging this into either equation, so we'll just stick with the first equation and change all of the y's into x's. So this will be 1 minus 2x times x plus x squared is equal to 0. So that's 1 minus x squared. Once we combine the like terms, is equal to 0. Therefore, x is going to be equal to plus or minus 1. That tells me that we're going to see critical points at 1, 1 and negative 1, negative 1 due to the fact that we got this by plugging in y equals x. Similarly, if y is equal to negative x, that's the other result from here, we'll go ahead and change all of these y's into negative x's. So it'll be 1 minus 2x times negative x plus negative x quantity squared. That's all equal to 0. Once we combine like terms here, we'll see 1 plus 3x squared is equal to 0. Solving for the x squared term would give us x squared is equal to negative 1/3. Now that is not possible using real numbers, so we'll say simply there are no real solutions. Now with that in mind, it is considerably more difficult to try to interpret this thing graphically if I have absolutely no idea what the graph looks like. So how do we figure out whether these critical points are maxima or minima or what? Well, we'll introduce that in the next video.